This is 6.2.43. We're now going to find the response of the same difference equation, but this time we are going to use the difference equation. And by using the difference equation, basically it means that we are going to ask you to write a code to simulate the output. We'll now show you how it's done on this part of the figure, which is basically a MATLAB code. You can also use a Python code. On the left part of this is when we are using input equals to 1. Remember that we have two inputs. The inputs to the system is 1 as well as 1 cosine 0.1 pi n. In fact, the real input is not 1 but unit step. So that means 1 from n equals to 0 onwards, as well as a cosine multiplied by unit step. So my inputs are causal. So here on the x-axis or horizontal axis, which is time n equals to 0 to infinity and nothing, or should be the input is 0 before that. Right, so the blue dots is un, and these blue dots are the un. So we have broken the input to two parts, and we'll study them individually. So how do we do this? Well, let's look at the code now. I'm going to test different terms. If I test term 1, it means for un. If I test term 2, it means cosine 0.1 pi n. So let's see how we do it for the first one, which term is 1. Now I'm going to use only for 30 samples, and then what I do is that I write this code, which basically says that if I'm going to use test term 1, I'm going to use omega to be 0 pi. If I'm going to use test term 2, it's 0.1 pi. Okay, you ignore line number 19 and 24 first. So if I'm going to use Fourier analysis, I have to substitute the correct omega. So this W comes from line 18 as well as line 23, setting different terms. So H will calculate for me the gain and phase shift at that particular frequency using this H. So this H is basically H is equals to Ej omega divided by Ej omega minus 0.5. This equation came from this page number 4, where we plug in the Z transform and set Z equals to Ej omega to get this equation here. And this is our frequency response, H omega. So now we know that if we want to evaluate omega for different frequency, all we need to do is to write the correct omega. So in our example, omega equals to 0 or 0.1 pi. Now, what about the difference equation? This is the for loop. I use 30 samples, and then I'm going to calculate different cosine for different n. Now, you must be wondering, why am I saving it as x of n plus 1? And the reason is that MATLAB, unfortunately, index from 1 to infinity. So it cannot have x of 0. So x of n plus 1 is really the term x of time at 0. Okay, anyway, we are going to use cosine 0.1 pi or cosine 0 times n. So omega depends on whether it is 0 for the unit step. The reason is that unit step have no change of frequency, or 0.1 pi. Okay, so this is, remember how we initialize omega. And once we have calculated the different x, the input, then we plug into our difference equation. So isn't this equation nothing but yn equals to x of n plus 0.5 y of n minus 1. Okay, so you might be confused with the notations because we are using n plus 1 for MATLAB, but this is the equation we are implementing. And we store the past value, n minus 1 here as memory, and then we do keep on looping. Alright, now this is the steady state response by Fourier transform. So I'm using the reference gain and the phase shift of my input signal. Okay, so where do I get my gain and phase shift? Which was from this equation here through the Fourier analysis. And I do this loop 30 times for my n sample, see? And then now I plot all the 4 figures. So here, be careful. I'm starting from index 0 to n minus 1 to plot the x. So this little n shows the horizontal axis of time. Alright, let's now explain these 4 figures. This blue dot here is the input, and it has value 1. This green dot here is the steady state response. So that means when the input is 1, the output is already 2 all the way. What about these circles going up? And then after that, it becomes the same as the steady state response. So here, this part is the transient condition, and the transient occurs because basically your difference equations have some memory, and initially the memory is 0, so it builds it up. And this circle and the star comes from 2 different ways I've calculated it. One is through the difference equation, and one is through the Z transform. So notice that the difference equation and the Z transform can capture the transient, while the frequency response only have the steady state response. So using this figure, we have seen this effect. You can also see it from the cosine 0.1 pi. So again, my blue circle is cosine 0.1 pi with amplitude 1. And my green guy here, and then after a while it becomes the same as the rest. This green guy is the steady state response. Well, this, now I'm going to shade it using maybe red. This is the transient. So in the beginning, this red and this green bars here don't meet because the transient has not died down yet, but after about maybe 5-6 samples, both these green bars and these circles meet and they become the same. Alright, so go ahead and see how I have plotted these 4 figures and where did they come from. In the next slide, I'll explain how I get the transient, the Z transform equation representing the output. And you will see this. The Z transform output consists of 2 terms. This is a steady state response, 2 multiplied by the original input, minus 0.5 dot to the power of n. When n goes to infinity, this term goes to 0. So this guy is introducing the transient for input equals to 1. What about for the sinusoid at 0.1 pi? This is 1.829. You'll realize that this is a steady state response gain, and this is a steady state response frequency phase shift. What about this guy? Again, 0.5 to the power of n. When n tends to infinity, this guy goes to 0. So this is the term for the transient condition that can be calculated using the Z transform. And this term dies down after, in our example, we show that in fact after maybe about 5-6 samples is finished. Okay, that's it. Thank you.